Hello everyone. So in this video I'm going to go through this problem. So we do have a beam which is a horizontal element here, and then we do have a vertical element of that beam. So we are not interested in that vertical element, but we are interested in that horizontal element. So in the first requirement here, we are asked to draw the free body diagram and the internal forces diagrams for the horizontal part of that beam. So we have a vertical part and we have a horizontal part. We are interested only in the horizontal part. So same to that the traffic light example that we explained in the lecture, and same to the examples that we did before, we are not interested in that horizontal element. We're only interested in that vertical element in the traffic light example. Same as here. We are not interested in that part. Instead, we are interested in this horizontal part. So I want to remove that part and put its effect on the centroid of that beam so that I can study the beam. So first of all, I can't deal with inclined forces. And instead, I need to do a resolution here and put this force in x and y. So what I will do, I will remove this 6 caps and I will put 6 cosine 35, and then I do have 6 sine 35. And now I no longer need this inclined load. So 6 sine 35, I do have 3.44 kips, and 6 cosine 35, I have 4.92 kips. Let me put it here. Okay, now since I do have now horizontal force and vertical force here, I want to take them and put them here, okay? But again, when I move a force from one location to another, I move it with a bending moment. So let me first draw the free body diagram. So for that beam, I do have this horizontal beam, and I do have a force here, 4.29 kip, and I do have a vertical force here, which is 3.44 kip. And when I move this force from one location to another, I'll move it with a bending moment. So as if I want to take bending moment at this point. So what do I have? I do have 4.92 times that distance. So 4.92 times 8. I will not take 3.44 because there is no distance to multiply this 3.44 with. So I do have a bending moment, and I will draw the bending moment in a way that we used to draw. I will draw the curve that is warping through the beam, and then I either have to draw the arrow above or below, and I will draw it below because that's how the 4.9 is rotating about this point. So the bending moment is going to be 4.92 times 8, and I'm getting 39.36 kip inch. Okay, and I do have a fixation at the end here. So remember, we are interested, if we look in the problem, we are interested in finding the shear stress and normal stresses at ABC. So ABC is somewhere here. So keep an eye on that section. Okay. So this is the free body diagram that I have. Let me write it FVD now. And let's now draw the axial force diagram and shear force diagram, bending moment diagram, which are internal forces diagrams for this beam. So I do have 3 lines here. This is AFD, axial force diagram, SFD, shear force diagram, and here is bending moment diagram. AFD, I do have kips, shear force diagram, the units kips, bending moment, kip, inches. Okay? You have 2 options. Either to draw diagram from right to left, because it's a free end, or if you might be confused with this, you need to get the reactions at this fixation, and you can start from left to right. Whatever is easy for you. So I will do the easiest way. Of course, not the easiest way. The easiest way is to start from the free end here. But if you're confused, let's get the reactions. So the fixation here, I do have 3 unknowns. I do have here x, y, x, and then I do have a bending moment. If you took summation of y equal to 0, you have 3.44 that looks up, and then plus, let me name this point m. So this is my. So my is equal to 0. and then I will find that my is equal to negative 3.44, which tells you that my assumption here was wrong. I need to assume it down, and 3.44 kept. Okay, axial force, I'll take summation of x equal to 0, and then I do have mx here, not momentum at x, it's just mx, the unknown, and I have mx plus 4.92 equal to 0. And also mx is gonna be negative 4.92 kips, which means I assume the direction in the wrong direction, so I'm gonna put the arrow this way, and mx is gonna be 4.92 kip. Now I want to find now the moment at m, and this will be equal to, I want to take now summation moment about m equal to 0, and I'll assume anything that goes clockwise positive. So I do have this 39, which clockwise, I will say 39.36. Of course, I'm not going to multiply by distance because it's already a moment. And then minus 3.44 times a distance. So the distance here, okay, let me tell you something. I didn't give you the distance here. So this distance was not given. So what should you do in that case? So in that case, I want you to consider this point M as if you're putting this fixation here. So as if what I'm doing, as if I'm taking this guy and putting the fixation here. Okay? And at that section, we want to calculate, we will later calculate the stresses at. So if you're not given any section here or any distance here, take this fixation and put it here. Okay? Because again, it's gonna be the same, because if you put the fixation here, as if you're telling me at that point there is x, there is y, and there's bending moment, and that's the case, because if you cut at any point within the beam, if you cut here, and we did that before, we had shear, we had axial, we had bending moment. So any point in that beam feels shear, bending, and axial moment. So in that case, I will move the fixation to that section. Okay, and now if I want to calculate the bending moment, I will get 3.44 times distance, 16 inches now. And what else do I have? Do have moment, I do have 3.44, 4.2, 4.92, I'm not going to take it because there is no distance to multiply 4.92 with. And then I do have the last thing, which is the bending moment. And it's going to be minus m because it is counterclockwise, equals 0. The m sub m, or the moment around m, I'm getting minus 15.68 kip inch. And minus here means that my assumption here was wrong, so I need to just adjust the arrow. So now m sub m is equal to 15.68 kip inch. So let's draw it now. So let me start now from left to right. And again, I'm going to take this fixation and I'm going to move it here. And I'm going to erase this. Okay, so here's the beam. Here is the point where I want later to calculate the stress at, so I'm going to take the internal forces at this point. Okay, now I do have a shear, so let's draw the AFD first. So the AFD, I will put my hand here. My hand gonna feel this intention, which is 4.92 intention. So I'm gonna go up, and it's gonna continue constant because there is nothing that's gonna affect it. Plus 4.92 kip. Okay, shear force diagram. What I do see, I'm gonna start with left to right, and I'm starting with 3.44 down. So 3.44 will start down, and it's gonna continue constant because there is no shear in between. Minus 3.44 kip. And lastly, the bending moment. So the bending moment, since we draw the arrow that's warping toward the beam, so the curve warping towards the beam, so the arrow gonna tell me whether the bending moment is up or down, and the bending moment here is up. So I'm gonna go at the beginning. It's not 0 because I do have concentrated bending moment here, equal to 15.68, and it's up. And at the end, if you notice here, the bending moment is down. So I need to end my bending moment down here equal to 39.36. But let's leave it here. Let's leave it. Let's calculate the bending moment at the end using the shear force. So let me just say at the end here I gonna name it N. So I want to find the moment at N, so I'm gonna say 15.68, which is this moment, minus the shear area. So the shear area is 3.44 times 16. So what I'm getting minus 39.36. And 39.36, that is actually as if I went down here. So this is 39.36, and this also agrees with this value at the end, 39.36. And I will just connect the bending moment like this. Okay, let me just erase this guy. Okay, and this is positive and this is negative. Okay, now I'm done with the internal forces diagrams. Let's now move to the second requirement here, calculate the normal stresses and shear stresses at ABC. So now I know this section that I need to focus on or like to work on, which is this guy, which is here. Okay, let's draw the section. So the section is this guy. So here's the cross section, and here's the point where I want to calculate the stresses, which is A, and at the centroid here is C, and lastly B. I knew it's at centroid because the whole height of the cross section is 3 and half of it is 1.5, so 1.5 is the centroid. Okay, so now it's missing something. Where is the axis of bending? Because later I want to calculate the moment of inertia about whether it's here or here. So let's look at the beam. So if this beam in the 3D, and I do have a force like this, so this beam is gonna bend that way, right? 1 minute, like this, right? So it's bending about, let's just assume our axes. So if this is X, and this is Y, and this is Z. So now you agree with me that when this beam in 3D, when it's gonna rotate due to this bending moment or this force here that wanted to rotate it that way, so the beam gonna rotate like this. So it's gonna rotate around X-axis. So where is X-axis? X-axis is gonna be this way, which is, if I drew the cross section, here is X. So X is parallel to the 0.8 dimension, which is here. So here is the axis of bending, XX, and now the axis of bending is here, XX, which is, this is the axis of bending, okay? And after getting the axis of bending, let's now put the axial forces, the shear force, and bending moment diagram on that cross section so that I can use these in the stresses calculation. So I do have a bending moment. I want to study this section, which is this section here. So this section has an internal forces of here, here, and here. So the section feels axial force equal to 4.92, and it's gonna act at the center. So I'm gonna write M is equal to 4.92 kips. Okay, it's in tension, so it's positive here. For the shear force in the cross section itself, it's not gonna matter. I know that it's vertical shear, so if anyone put it up or down, it doesn't matter as long as the shear is vertical. But it's gonna matter later the direction when we talk about the stress element. So let's now fill this by saying, okay, V is equal to 3.44 kip, which is here, 3.44. So this section, at this section, I do have 3.44. Finally, the bending moment. So the bending moment at this location, where that section is, I do have a moment of 15.98, and the moment is up, which means the arrow is up. So I want to draw another arrow here, and that is for the bending moment. So M is equal to 15.68 kip inches. Okay, let's now put in the diagram or in this graph the signs that is for the moment and for the axial force. For the moment, this two quadrants gonna feel negative, and the bottom two quadrants gonna feel positive due to bending moment. Due to axial force, let me put it in black here, and the sign's gonna be in black. So I had tension, so everything is in tension. Okay? So let's now calculate the normal stresses. I'm gonna calculate the stress at A. So I will say normal over area, so normal force, which is 4.92 kip over area, 0.8 times 3, and it's gonna be positive because at point A falls in that region where the normal force is positive. Then minus moment, which is 15.68 kip inch, y, which is distance from the centroid to point A, it is 1.5, over the moment of inertia about the axis of bending. So parallel 0.8, perpendicular 3 cube over 12. And I'm getting negative 11.02 KSI. Do the same thing for B. So I'm gonna copy this and I'm gonna use it for B, but I'm gonna change some signs. So the normal gonna be the same, positive, and the moment should be positive. And the value here gonna be positive 15.117 KSI. So also the question asks us to also calculate the normal stresses and shear stress at A, B, C, and at the location of the neutral axis. So at the neutral axis, of course, the normal stress is equal to 0. But if we want to find where the neutral axis is, the neutral axis is going to fall in a region where we have positive and negative. So it's going to be somewhere here. Okay? So this is the neutral axis. And if I want to find it, I'm going to take this equation, copy, and I'm going to put it here. I'm going to say 0 is equal to positive n over a, and then instead of having a distance y, I'm going to set it here. So the whole equation now has one unknown, which is y, which is distance from the centroid to the neutral axis. If you solve for y, you are getting y is equal to 0.235 inches, so that you know that this distance is 0.235 inches. Okay? So let's draw the normal stress distribution. So I'm gonna make the reference line horizontally like this, and not the reference line, sorry, like this is the working lines, and then the reference line is gonna be vertical because it's parallel to the bending moment, because that's how the moment distribution in that cross section. At point A, or at the upper parts, I do have negative 11, so I'm gonna go to 11 here, 0.02, and at bottom I have 15. So let's connect them, and here's 15.117 KSI. The top is in compression, the bottom is tension, and I'm gonna say this is normal stress distribution. Okay? Now, the second part is I want to calculate the shear stresses. So the shear stress, we want to calculate it at 3 locations, at A, B, and C. So you know that at A and B, it's equal to 0 because they are at the edge. And now I want to calculate it at the center. If you remember, for rectangle sections, at the center or centroid, not the neutral axis, centroid, it is 1.5 V over area. If you remember that, then use it. If you don't, then it's okay. Use the VQ over IT. So the shear was equal to 3.44 kip. Q is, we want to find this at the centroid, right? So we want to cut at the centroid now, and we do have 1.5, which is this height, times 0.8 times 1.5 over 2. So 1.5 times 0.8 times 1.5 over 2. Over the inertia, which is 0.83 cube over 12, times thickness, which is 0.8 inches. You are going to get 2.15 KSI. So you either use this or use the 1.5 V over area. Lastly, I wanted you to calculate the tau at the neutral axis because I have a point here which tells you that the maximum shear stress happened at the centroid, not at the neutral axis. So where is the neutral axis? Here. So I want to find the shear at this. So what I'm going to do basically, I'm going to calculate the remaining distance. So I found that this distance is 0.235. So I'm going to say 1.5 minus 0.235, and I'm getting 1.265. Okay, so I want to find the shear stress at this line, so I'm going to cut in here, and I'm saying 1.265 times this distance times the distance from the centroid here, which is 1.265 over 2 plus 0.235. Okay, so let me write that down. Now it's not 1.5 V over area, it is just VQ over IT now. 1.5 V over area is only valid at the centroid. So I'm gonna say 3.44 times 1.265 times 0.8 times 1.265 over 2 plus 0.265, right? Is it plus 0.235? My bad. Okay, over the moment of inertia, and the thickness is gonna be the same. And you are getting 2.097, which obviously tells you that the shear stress at the neutral axis is less than at centroid. So the centroid is maximum. At the neutral axis is something different. So let's plot this. So I'm gonna have a vertical, the reference shear is vertical because the shear is vertical, and I will simply extend this centroid line because I know that's at the maximum shear, and I'm gonna make a parabola that goes like this. Let me make it in red, and like this. And the shear here is equal to 2.15 KSI, and at the neutral axis here is 2.09 KSI. And this diagram is called shear stress distribution. Okay, now finally, I want to find the stress element. So calculate the stress state and draw the stress element for ABCD. So ABC. So at ABC, I want to find the stress elements. We already calculated the stresses here, so let's find the stress element. So I'm gonna draw it here. So stress elements, I'm gonna say at A, I'm gonna have this square, and I'm gonna do this for B and C. B and C. So at A, so at point A, which is here, when we want to find, and here is C and here is B, okay? When we want to find the stress element at certain points, we cut at that point. So what we are left with when we cut, we are having, for example, this is the beam in 2D, and here is the stress element at A, and here is at C, and here is at B. Okay? For the shear, let's first of all start with the shear at A. So when we cut in here, we already found that the shear is 3.44 from that surface. So 3.44 is applied to that face from the very beginning, 3.44. Okay? So since I do have 3.44 here, 3.44 as a force, and then the shear direction is going to be here because the shear is going to be something like this. So for all of them, the shear is like this. But notice that, where is A and B and C? So A, C, B. So here is A, C, B. At A and B, because they are points, I just exaggerated by drawing the square big, but like at A and B, the shear stress are equal to 0. So I'm gonna erase them at A and at B. And then at C, I do have the shear like this. So if I know one of them, so I know all of them, the directions. And the tau is equal to, at C, 2.15 KSI. Okay? Okay, let's now do the axial force. So for A, B, and C, I when I drew the normal force distribution, it was something like this, right? So let's look at the normal stress distribution. So at point A, I do have a negative stress of 11.02. At C, which is at the centroid, I have some stresses here. I don't know what that is, but I can calculate the stress here either through the similar triangles or I can calculate the stress. So let's do this. So I want to calculate the stress at C. So C, where does C lies? C lies in a region where I have positive and positive. So I'm gonna use this equation. Okay, but notice that C is at the centroid, so the y is equal to 0. So if y here is equal to 0, then this whole term is equal to 0, not the normal stress. It is just the second term is equal to 0. And sigma C is equal to 4.2 over 0.8 times 3, which is 2.05. So some people might use that equation, and other people can just use these similar triangles. So this stress is equal to 2.05 KSI. Okay, so at point C, I do have a stress is equal to positive 2.5, and then at the end I have 15.117. So here, as if it's positive, here is negative. So here I do have negative stress at point A. Point C and point B, I have positive stresses. So I'm gonna put at A, I do have compression equal to 11.01, which is here, or O2, KSI, that's sigma X. And then for C, it is in tension, and for C and B and C, they're in tension. So for B, which is down, it's equal to 15.12 KSI, and for that guy, for C, 2.05. Is there stress in y direction? No. So I'm done with that step. Lastly, I want to rotate. I said in the question here, rotate the stress element at B by 45 degrees, but it's not B, it should be C. So I'm gonna update this, it should be C. So at C here, I want to rotate it by 45 degree. So let me write the stresses at C. So stress at X is equal to 2.05 KSI. Shear stress XY is equal to positive 2.15 KSI. Stress in Y is equal to 0. And I'm gonna use the equations that we had in the lecture, just copy them and we can use them. Here, I'm gonna copy and put them here, and I'm just gonna plug and chug. Okay, but before plugging and chugging, I do have, this is the stress at C. The directions or the axis here was X and Y. What I want to do, I want to rotate this element by 45 degrees. And it's positive 45 degrees, so it's counterclockwise. And here is the new element. Okay, and I'm rotating from X, it's gonna go to N, so this is N, and perpendicular to N is T. Okay, so now let's find a stress at N. A stress at N is equal to stress X plus Y over 2, so I will say 2.05 plus 0 over 2, plus 2.05 over 2 cosine 2 theta, and theta is 45 degrees, plus tau xy, which is 2.15 sine 2 times 45 degrees. And if you solve for this, you're going to get 3.175 KSI. Okay, this is for stress at N, and it's positive, so I'm going to put it that way. Stress at N, 3.15 KSI. Okay, now I want to find, let's get the shear first. So shear N and T minus stress at X, 2.05 plus 0 over 2 sine 2 times 45, and then plus tau xy, which is 2.15 cosine 2 times 45. And when you solve for this, you're going to get negative 1.125 KSI. And it's negative, so the shear going to be negative that way. Tau nt is equal to 1.125 KSI. Now, what is missing is stress in T. So as we said in the lecture, stress in T is going to be same equation, stress in N, but instead the theta going to be 90 plus that theta. So stress at T, I'm going to, instead of using 45, I'm saying 45 plus 90. And here, 45 plus 90, which is 135, and 135. So I'm going to erase this, and I'm going to put 135. And if you solve for this, you're going to get, oh, my bad. So this is instead of 1.125, this should be negative 1.025, and here is negative 1.125 KSI. So here the shear should be 1.025, and the stress in T, it is negative, which means compression, and it's equal to 1.125, and here 1.125. Okay, if you have questions, email me. Thank you.